So in this lesson we were talking about an introduction to probability, and a probability and a percentage are very similar and can sometimes mean the same thing, but a percentage is often something we've learned to be more of a fact in the past. So if I say 80% of the folks in our class are computer science majors, that's a fact. That means I've counted everybody and I've tallied up the number of people who are computer science majors, divided it by the number of people who are just in total in the room. But let's say I do something different. I randomly select somebody from the class. I can now say there is an 80% chance that I select a computer science major to win the prize. And of course, when we think about that, we might say, well, either you do or you don't. And so that's 50-50. But that's not valid, because we know that it's more likely, since my class is full of computer science majors, that I randomly select a person and it ends up being a computer science major than somebody who is not. So this means if I were to repeatedly randomly select someone from the class, I can expect that 80% of my selections would result in some in computer science majors. So this percentage actually just describes something that would happen, that we expect to happen in the long run if we repeatedly did the same thing over and over again. As far as how we work with probabilities in comparison to percentages, it's exactly the same. Okay, so probability is just an extension of counting, and in that what I mean is, let's say that we toss a coin 2 times and we want to get exactly 1 head. So that means either heads tails or tails heads. Now there are 2 ways that we can get exactly 1 head, and these are those 2 ways. That's where our counting problems usually stopped. But now I want to compare it to the total number of possible outcomes. So there are 4 possible outcomes, those being heads heads, heads tails, tails heads, tails tails, and 2 of the 4, or 50% of the time, I should get exactly 1 head. Either the head in the first position and a tail second, or vice versa. So a probability is defined as, if you have some event E, I would describe it as kind of a set. It's a set of all possible ways you get what you want. And S is the set of all possible outcomes, including the ones that you do want and do not want. Then we can find the probability of E by counting the size of the number of ways we can get what we want, divided by the size of what we call our sample space, or the set of all possible outcomes. So in our case, the size of the event was 2, because there were 2 ways that could happen. If I actually wanted to list out those 2 ways, I could say set E contains H, T, and TH, and the sample space contains all 4 of them, but the size is 2 for how I can get what I want out of the 4 possible ways. So I could say 50% of the time I would expect to get that outcome. Now we can combine our counting techniques, like let's say in this case there are many lotteries now that award enormous prizes to people who correctly choose a set of 6 numbers out of some number of integers, usually between 30 and 60. What's the probability that you correctly pick the 6 numbers out of 40? Well, if you're talking about a lottery, you're not going to pick the same number twice, so there's no repetitions allowed, and also the order doesn't matter. Order does not matter. So what order you told the clerk the 6 numbers that you wanted is not going to make a difference in terms of whether or not you win. So the number of ways you could correctly guess the exact 6 numbers, well, that's going to be 1, right? There's only 1 way you could get the right 6 numbers, meaning that it doesn't matter what order you pick them in, but if the winning numbers are 1 through 6, then 1 through 6 is the only way you could win that game. Now, alternatively, you could say, from the 6 winning numbers, pick all 6 of them, and that's going to give you 1 as well. For the sample space, we're saying, well, what's the set of all possible 6 number combinations? Well, again, if order doesn't matter, then from the 40, pick any 6 of them, and the probability of your event will be the number of ways divided by the number of ways. I'll leave it like this. This is going to be very, very close to 0. I think it's something like 0.0000026%. So there's a very, very small chance you win the lottery. Let's look at another one where we have to combine counting techniques. A hiring committee of 5 people is to be formed from 8 females and 9 males. What is the probability that 3 members are female and 2 are male? Well, first of all, the number of ways my event could happen is I need to figure out the number of ways I could get 3 females from the 8. That's going to be combination, because again, we're assuming the hiring committee is full of equals. From the 8 females, how many ways are there to pick 3 of them? From the 9 males, how many ways can I select 2 of them? And then I want to figure out how many total groupings there are with all of the female groups and all of the male groups. So I'm going to multiply these together. My sample space is going to say, well, how many different groups are possible? Well, that just means that from 17, if we select any 5, there will be 17 combination 5 different ways that you could just form groups of 5 people from a total of 17, regardless of sex. And then the probability of E will be 8 combination 3 times 9 combination 2 divided by 17 combination 5. Okay, a hiring committee of 5 people is to be formed from 8 females and 9 males. What is the probability at least 1 female is selected? Now, at least 1 means I could have 1 female and 4 males. That's at least 1. That's exactly 1. I could have 2 females and 3 males, 3 females and 4 males, or 4 females and I'm going the other way. This should be two males, and then 1 female, 1 male, or one more, 5 females and no males. That would also constitute having at least one or more females. Now there is a 6th possibility, but that's not the one I want. That would be where I get 0 females and all 5 are males. So I want to figure out the number of ways to get any one of these 5, and I don't want the counts involving having the 0 females. So if I look at the number of ways of selecting 5 people from 17, I believe that comes out to 6,188. What I can do is I can add up these. I can sum up those, right? Because they're non-overlapping. So the number of ways of getting 1 female and 4 females plus the number of ways of getting 2 female and 3 male and so on, that would give me some part of this 6,188. If I add all of them together, the sum would equal 6,188. But instead of adding up just the ones that I want, because there's more of them than the ones that I don't want this event right here, I can actually just count the number of groups that would end up with all male and just remove that from the 6,188. So what I'll do to calculate that is to have an all male count, group count. That would be from the 9 males, all 5 people selected are from that group, and that comes out to, let's see here, 126 groups of all male. So I don't want those. Those are the only groups that I don't want to form. I want a group with at least 1 female. So the probability of getting that event would be the number of ways we get at least 1 female, which is 6,188 minus the ones that are all male out of the 6,188. And that's going to be pretty close to 100%. So we should get at least 1 female because, half of the people in the group of 17, nearly half of the people are female. So if we were randomly selecting, we would have a high chance of selecting at least 1 female, which is why this ratio will be close to 1. Let's look at another application. In this case, consider all bit strings of length 10. So what we're dealing with here is 10 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One possible one would be 1, 0, 1, 0, 1, 1, 1, 0, 0, 0. I'm just making that up. That's just one possible sequence. Now, I want to know what's the probability of getting at least 1, 1. Well, again, that means 1 or more 1. 1 or more 1. let's see how many possible outcomes there are. Well, at each juncture, my first digit could be a 0 or a 1. If I got a 0 at the first digit, the second one could be a 0 or a 1. If I got a 1 on the first digit, I could have 0 or a 1. And what we see here is that there are 2 branches, each having 2 branches. And if you imagine this tree going out to 10 branches, doubling out each time, this is going to be 2 to the 10th power. 2 possibilities at each juncture, 10 possible slots. This is going to be 2 to the 10th. Now, how do I get what I want, which is strings with at least 1, 1? Well, I could have, again, similar to up here, I could have, to get at least 1, 1, I could have, for the number of 1s, I'll just write like this, and the number of 0s, I could have 1, 1 and 9 zeros, or I could have 2 1s and 8 zeros. Okay, I have at least 1, 1 in each of these cases. I could have 3 1s and 7 zeros, all the way up to I could have all 10 1s and 0 zeros. Okay, that means I have to count, do 10 separate counts and add them all together. Or I could consider the only case that I don't want. The only case that I don't want is where I end up with no 1s and all 10 zeros. Okay, how many different ways are there for me to not get what I want? Well, there's only one sequence that consists of all 10 zeros, and that's the sequence 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So there's only one way to not get at least 1, 1. So again, rather than adding up all of the things that I don't want, I'm just going to remove, that I do want, I'm just going to remove the ones that I don't want from the set of possibilities, which is going to give me, well, there's 2 to the 10 possibilities, minus the one that doesn't constitute having at least 1, 1. And so my probability of that event will be 2 to the 10th minus 1 over 2 to the 10th, which comes out pretty close to 100%, right? 1 out of 2 to the 10th that doesn't constitute having at least 1, 1 is very, very small. Okay. Couple more things here. So now let's look at the probability of joint events. So for things to happen jointly means they both happen. All of the things, all of those events happen. And these are separate events. So we're taking more than one event and asking what's the likelihood that all of those happen simultaneously. First of all, a little definition here. We say that events are independent if the probability of one event is not affected by the occurrence of another event. So an example of independent would be 2 coin tosses. The first event, being the first coin toss, is going to have no influence on the likelihood of what happens in the second coin toss. An example of dependent events, on the other hand, would be where the probability of one event is affected by what happened first. So maybe drawing 2 people without replacement. Okay, so if there are, say, 10 people in a pool, and I draw one of them, well, now there's 9 people, and now your probability of winning, assuming you haven't been drawn yet, is now 1/9 instead of 1/10, because that person can't be reintroduced. Let's do a basic computation with this and realize that this is just taking percentages of percentages. Suppose 40% of students in a classroom are female and the rest male. Further, suppose that independently of sex, so that the probability of a student having an Apple Watch is not affected by their sex, 25% of students have an Apple Watch. What is the probability that a person is male and has an Apple Watch? Well, let me just start off with 100 people. Okay, so we know that 40% of them are female, and we know that, 60% of them are male. So 60% are male, because we want to ask what percentage are male and have an Apple Watch. Well, 60 males are in that group, and then regardless of what sex you are, 25% of that 60 males should have an Apple Watch. So 25% of that would be 15 males with Apple Watch. Okay, well, what did we really do here? Well, if I want to know the probability, this would be 15 out of 100, which is 0.15. Well, really what I've done here is I've taken 0.6 times 100 times 0.25, all of that times 0.25, and then I divided by 100. Now, look at that. Well, if I multiply and divide by 100, those cancel out. And really what I ended up doing was just taking 25% of 60%, which gives me my 0.15. So this leads to the rule for joint probability. The joint probability of events is the product of the corresponding probabilities. Joint probability means that all the events occur. It makes sense to write the probability of A. Now, because we often deal with events as being sets, this is the intersection of, but you can read this as and, right? We want basically the overlap of those two events. And that's going to be the product of the two probabilities, and it's the probability of A times the probability of B. But we need to also just consider whether the likelihood of B happening has changed because of A occurring. I'll give you two examples of this to help you illustrate better. If the events A and B are independent, then the probability of B taking into account event A is just equal to probability of B. We don't need to really worry about the fact that A has happened. So imagine rolling a 6-sided die twice. What is the probability that neither rolls result in a number divisible by 3? Okay, well, let's think about the outcomes and see which ones are divisible by 3. So we don't want a roll that's divisible by 3. Well, 3 is divisible by 3 and 6 is divisible by 3. So the probability that on the first die, I'll define this as the first roll is divisible, the second roll is divisible, and I want both of those things to happen. So this is going to be 4, 6 times 4, 6, right? In other words, if I didn't get a number that's divisible by 3 in my first roll, that doesn't change the probability that the second roll is divisible by 3, because the die doesn't remember what happened. So here we get 4, 6 times 4, 6, or you can write it as 2/3 times 2/3, or 0.67 times 0.67. Again, 67% of 67% of the time, we're going to get neither die being divisible by 3. So I think I'll just leave it like that. Okay, now let's consider a situation where that probability is, the probability of the second outcome is affected by the first. Suppose you enter a raffle and you can win one of two prizes. You and your friend both want to win a prize. There are 20 people in the raffle. What is the probability that you both win? Okay, well, if you think about it like this, this is the probability that you and your friend win, that you both win. So what percentage of the time will you win? Well, we can think about it as this way. The first person or the first prize could be given to either of you or your friend. Now that's out of 20 people. But now one of you, assuming one of you got the first prize, now the probability that the next person gets the prize is not, there's one of you left, right? So that's already changed, but there's not 20 people in the raffle anymore. You can win one of two prizes. Well, now there's only 19 people left. And so we end up with 2/20 times 1/19. And this is the probability that, I don't know, you win given someone has already won. Given your friend has already won. Now this comes out to, if we were to calculate this, just to show you one other way you could do this problem instead of having to multiply probabilities, you could do 2 out of 20 times 1 out of 19. This comes out to about 0.0053. Now here's another way I could think about this. I could do this with combinations. I could say, well, for the numerator, the probability that you both win is from you and your friend, select both of you, right? Or I could do a permutation. I'll show you that both of them result in the same thing. Divided by the total number of ways 2 people out of 20 can win. And if I do this, not surprisingly, I get 0.005. Now, if you were considering order, you could also write this as assuming, the prizes are different, permutation 2, 2 divided by permutation 20, 2, and guess what? You're still going to get 0.005. With combinations and permutations, as long as you're using the same thing in the numerator and denominator, you're going to get that nice cancellation of the fact that a combination, both of these divide by permutation 2, 2. Anyway, long story short, they cancel out. But you can do it as multiplying the probabilities together, or you can do it by using counting methods. Okay, example 9. An administrator at a college determines there is a 90% chance that a student has their student ID when asked for it. There is an 8% chance they have their passport. They need to have one or the other in order to receive the services they are requesting. What is the probability that the student will be served? Well, I'm going to introduce you to a way of actually figuring out all the possible outcomes here for a student. So a student, I'm going to draw a little tree diagram, will either have their ID, and I'm just going to refer to that as, I'll just say I. So you either have your ID or you do not have your ID. I'm going to put that little bar over the not ID. And I know that there's a 90% chance that a student has their ID and 10% chance they don't. So think about it this way. You have a group of students, 90% of them are going to walk along this path, 10% are going to walk along this path. Now, we're assuming, we kind of have to assume that whether or not you have your passport is independent of whether or not you have your ID. So of the 90% who have their ID, some will have their passport. I'll just denote that with a capital P. Some will have their passport and some will not have their passport. Well, in particular, 8% will have their passport, which means the remaining 92% will not have their passport. Of the 10% who do not have their ID, 8% will have their passport and 92% will not have their passport. Now, the reason I'm putting this together in a tree diagram is, again, think about the multiplication principle. The only difference here is we're multiplying percentages. So 8% of 90%, 8% of 90% of people have both forms of ID. Both forms of ID. So 0.08 times 0.9 is 0.072. So 0.072, or 7.2% of this entire 100%, this entire whole, have both forms of ID. Now the other 92% of that, or 92% of 90%, which would be the, let's see, 0.9 times 0.92 comes out to 0.828. And we can do the same thing down here. 10% of 8% would be 0.008, and 10% of 92% would be 0.092. Now when you add these together, not surprisingly, guess what? You're going to get all 100%, that whole back, because we just kept dividing and branching people out until we could figure out what their status is on their ID and their passport. So 7.2% of all students have both forms of ID. And as another example, 9.2% of all students have neither form of ID. We want to know, what is the probability that the student will be served? Well, they're going to be served as long as they have one form or the other. So where do they have one form or the other? Well, here they have both, which is okay, right? You can have both forms of ID. This doesn't say you can't bring your passport if you have your ID. They'll still be able to be served. These 82.8%, they have their ID, just no passport. They'll be served. And these 0.008 or 0.8% of people have their passport, no ID. They will be served, but these 9.2% of people will not be served. So in total, that's really just one. Take away what you don't want, and that's going to be 0.9 0.08. So the probability that you're served will be 0.908. So what I've done here is there were two events. Each event either does happen or doesn't happen. Break it up into a binary outcome, and then continue branching out so that what we can do is group ID status with passport status, and then we just pick up what we want out of that chart. Makes it real nice and straightforward. One last example. If we know a student has his passport, what is the probability he has his student ID? Okay, if we know a student has his passport, so that must tell me something about the group of people that I'm studying. If I know a student has their passport, that means they're either in this group or they are in this group. So if I know a student has their passport, that is out of the 0.072 plus 0.008, right? That means out of that equals 0.08, or 8% of students have their passport. Well, that's not a surprise, right? Because we already knew that 8% of students have their passport. But out of those students, given that we know that a student is part of that 8%, what is the probability they have a student ID? Well, out of those 0.08 who have their passport, which ones have their student ID? Well, these ones don't, right? These ones don't. They only have a passport. But these 0.072 also have their ID with them. So 0.072 of students out of 0.08 of students with passports have their student ID. So this suggests 0.072 divided by 0.08 comes out to about 90%. Okay, so 90% of students with passports have their student ID. Now this should not come as a big surprise because we know that these two events are independent of one another, but this is what we call a conditional probability. Okay, conditional probability. This means that we're looking at the probability that you have your ID given, this means given that, or out of the people who have their passport. And that is actually 0.072 divided by just the percentage of people who satisfy the condition that they have their passport, which is 0.08, which comes out to 0.9, and it should, because we know that the likelihood that you have your ID is independent of the likelihood that you have your passport. So we'll stop there. These are just some basic counting principles applied to probability. Really the big difference here is lay things out, especially situations like this. Just draw that tree diagram. It takes a minute, and then you have everything before you visually. You don't have to remember what to multiply. You just have to be able to figure out what to pool together. And the reason we can add these is because, remember, these are distinct groups, and being at one end of the branch versus another versus another versus another, these are different groups of people, right? Because at each juncture, some students go this way, some students go this way. Then from that juncture, some students go this way, some students go this way, and similarly down here. So the reason we can add these together is because they're non-overlapping. These are four distinct groups. It's kind of like looking at a Venn diagram, and these are students with IDs, these are students with passports, and what we want is the students in here who just have IDs, no passports, who just have passports, no IDs, or people who have both. The only group that we don't want to include in there is the group of people who have neither of them.